Hi, it's Muzzer with another quick tutorial. This one on number 12 on the 4B worksheet. So we've got this elevator and a counterweight, and believe it or not, this is actually how elevators work. They have a counterweight that runs on the cable connected to them, so that all that the elevator actually has to lift is the mass of the passengers inside it, or the freight. So the counterweight does a lot of the work, i.e. gravity helps. So we're told that the elevator with passengers has a mass of 1,600 kilograms and the counterweight has a mass of 1,200 kilograms. We want the magnitude of the car's net acceleration as it falls from rest at the top of the shaft and their final speed, but we'll get to that. So I've drawn the picture here in case you weren't clear on how it would look, and we know that as the elevator falls, the counterweight rises and vice versa. So the important thing to know is that, first of all, we have to consider these two objects independently. So we're going to write a set of equations for the weight and a set of equations for the elevator. Let's start with the weight. It is true that on the y-axis, and that's all we're dealing with here, the mass of the weight is equal to the net acceleration of the weight. It's also true that on the y-axis, the force of tension minus the force of gravity is equal to the net force on the y. So we can, of course, set those equal to one another, and we get mass of the weight times net acceleration equals force of tension minus force of gravity for the weight. Okay. Well, for the elevator, it's true that the sum of forces on the y equals the mass of the elevator times the net acceleration. Here's one of the cool parts. The net acceleration for these two objects is the same. That's going to make our life a lot easier. So here's where it's tricky. Because the elevator is going down, we're going to make the force of gravity sort of essentially the positive. Oh, this sounds terrible. But the net force on the y-axis for the elevator is equal to the force of gravity minus the force of tension. Because the force of tension is what's opposing its motion. The force of tension is opposite the direction that the elevator is moving. Put these together and we get mass of the elevator times net acceleration equals force of gravity of the elevator minus the force of tension. Well, here's the cool part. We can actually add these two equations, and I will be the first to admit I didn't completely understand this. A student had to help me out. Thanks, Michael. What we're saying is that if this equals this and this equals this, then adding this and this is the same as adding this and this. Somehow this makes it simpler than just setting them both equal to force of tension and solving them each for force of tension and setting them equal. So once I've got this, I notice immediately that the force of tensions cancel out. This leaves me with mass of the weight times net acceleration plus mass of the elevator times net acceleration equals, well, I've got negative force of gravity on the weight plus force of gravity on the elevator, but I'm going to flip those so I don't have a leading negative. From here, I can go ahead and factor out my net acceleration, leaving me with A net times the quantity mass of the weight plus mass of the elevator equals force of gravity on the elevator minus force of gravity on the weight. Oh yeah, note, I flipped the force of gravity on the weight and the elevator so that I wouldn't have a leading negative. Well, now it's a pretty simple matter of dividing both sides by mass of the weight plus mass of the elevator. That gets rid of that, and I've just solved for the net acceleration. Now, to do the next part, the car's final speed, well, that's pretty easy. Since you have VI, and you have delta y, and you have acceleration, all you need is VF. Get going.